In the previous video, we have looked at one of the options to numerically encode information about small molecules, which is using transformer networks with small molecule smile strings as the model input. Another option for building small molecule prediction models or generating numerical small molecule representations is representing small molecules as graphs and using graph neural networks, which are neural networks specialized for processing graphs. First, we are going to look at how we can represent small molecules as graphs. We've already discussed this briefly when we looked at De Morgan fingerprints and the RDKit fingerprints. The atoms of a small molecule can be interpreted as the nodes of a graph, and the bonds of the molecule can be interpreted as the nodes of the graph. We next do a numbering of all atoms of the molecule, starting from 1 and going up to n, which is the number of atoms in the molecule. In our case, we have 14 atoms. How we assign those numbers is arbitrary. We can then calculate features for every atom and for every bond. For example, the features of the atoms can contain information such as the atom type, mass, and charge. Those features are stored in vectors xi, where I is the number of the atom that we assigned to the atom in the previous step. And all of those feature vectors can be stored in a matrix X of dimension n times dn, where n is the number of atoms and dn is the dimension of each atom feature vector. We also calculate bond feature vectors for all bonds and store these in vectors eij, where I and j are the numbers of the atoms that are connected by this bond. These vectors can contain information such as bond type and if the bond is part of a ring. All those bond feature vectors can be stored in a three-dimensional array or tensor of dimension n times de, where de is the dimension of the bond feature vectors. We then also use another matrix A to indicate between which atoms we have bonds in the molecule. This matrix is called the adjacency matrix, and an entry at position ij of this matrix is equal to 1 if there exists a bond between atom I and j, and the entry is 0 if there is no bond between those two nodes or atoms. We can now represent our graph using the matrices or tensors x, e, and a, and we can use these as the input for a graph neural network. We are now looking at how a typical forward process of a graph neural network looks like without going into details here. On the previous slide, we have seen that we calculate initial atom and bond feature vectors. We now typically update all atom feature vectors by using information about neighboring bonds and atoms, and we do this iteratively for a predefined number of steps t. If we look at a specific example for atom I, we update the feature vector xi by using information about the neighboring bonds and the neighboring atoms. And in each update step, we do this for all atom feature vectors in parallel. We update the features using update functions ut, which depend on learnable parameters. In a few slides, we will have a look at how those update functions can look like. After those t update steps, we have updated atom feature vectors that now not only contain information about themselves, but also about their environment. And this is not only restricted to the direct environment. If we imagine that we update xi for the first time, we only get information about the immediate environment. But since we also update the neighboring atoms in the same way, those atom feature vectors contain after those updates also information about their immediate environment. This means if we update vector xi again, we again only use atom feature vectors that are one step away, but because those atom feature vectors also contain information about all atoms that are one step away from these atoms, we can actually get information from atoms that are 2 steps away. And if we repeat this process, we get even information from atoms that are further away. After we have updated each feature vector for t time steps, we want to obtain a single vector that represents the entire graph or molecule. We can achieve this by using some kind of pooling function with all the updated atom feature vectors as the input. This pooling function can be the element-wise mean of all atom feature vectors, similar to what we have seen for our transformer network encoder. Or we could also take the element-wise maximum or the sum of all vectors. This gives us a single vector x that is now a numerical representation of the entire graph. This vector x is then typically used as the input of a standard feed-forward neural network to predict the property of the molecule. This can be either a classification or a regression task. And typically, this whole model, the graph neural network part and the feed-forward neural network, are trained simultaneously end-to-end. Here you can see the forward process summarized. We encode our molecule as a graph, we update our node feature vectors, and then we pool all updated node or atom feature vectors together to obtain a single vector x that is the representation of the entire graph. We can then use this vector as the input of the neural network to predict the property y of the graph. When we train such a model, we typically do this end-to-end, which means that we adjust the parameters of the update functions for the graph and the parameters of the feed-forward neural network simultaneously. And the training procedure is identical for standard neural networks, where we calculate the loss function for our predictions, then calculate the gradients for all learnable parameters using breadprop, and then we update the parameters of the neural network accordingly. We have also the option to pre-train graph neural networks in a self-supervised fashion. One way of doing this is very similar to how we can pre-train transformer networks. We could, for example, mask the type of specific nodes and then predict the type of the node by extracting information from neighboring bonds and atoms. This is similar to the mask token prediction task that we have seen for our transformer network encoders. But similar as to what we have seen for SMILE strings as the input for transformer network encoders, we could also calculate different molecule properties and pre-train the model to predict those molecule properties during the pre-training steps. So far, we haven't really looked at how those update functions of a graph neural network can really look like. We're now going to look at a particular graph neural network that is typically used for small molecules, the Directed Message Passing Neural Network, or short DMPNN. As before, we calculate atom and bond feature vectors for all atoms and bonds in our molecule. In a DMPNN, we then calculate hidden representations of all atom bond pairs. And we do this by first concatenating the atom and bond feature vector and then multiplying the resulting vector by matrix WH, where the entries of this matrix are learnable parameters. Then we apply the ReLU activation function to the resulting vector. In the following steps, we now want to update the hidden atom bond representations. Let's assume we want to update the atom feature or atom bond feature vector marked here in orange. To update the vector representing this atom bond pair, we use information about the neighboring atom bond pairs that move in the direction of the orange atom, here displayed in green. However, we do not include the atom bond pair that shares the bond with our atom bond pair that we want to update. In our case, we have two such atom bond pairs for the same atom. For this update step, we first calculate a so-called message vector for the atom bond pair that we want to update. This message vector is simply the sum of those vectors representing the green atom bond pairs. We then use this message vector to update the representation of our orange atom bond pair. We do this by using the initial representation of the atom bond pair and the message vector that we have just calculated. All atom bond pairs in the molecule are updated in the same way simultaneously, and we repeat this process for a predefined number of T update steps. Summarized, this is what we have so far. After T update steps, we have updated the representations of all atom bond pairs, and we now want to obtain a single representation for each atom. We can achieve this by first summing all atom bond representations that include this atom, and then using this vector together with the initial atom representation as the input for a single layer neural network. We concatenate the initial atom representation together with the representation Mi for this atom that we've just calculated. We multiply this vector by matrix WA with learnable parameters and apply the ReLU activation function. We now remember that we want to obtain a single vector for the whole graph using the atom vectors Hi. In a DMPNN, this is achieved by summing all atom feature vectors Hi element-wise. This vector x is now a representation of the entire graph or molecule, and we can use this vector as the input for a feed-forward neural network to predict a property of the molecule. After we train such a graph neural network for predicting a property of the molecule, we can use this as our final prediction model, since we trained it already for the task of interest. Alternatively, we can also extract after training for each molecule the vector x that represents the entire molecule. This vector is now a task-specific representation of the molecule because we trained the network to store all information that is relevant for the prediction task in this vector. We can then use this vector as the input for an alternative prediction model, such as a gradient boosting decision tree model, which we train for the prediction task of interest. Depending on the prediction task, this might lead to improved model performance. Here we can see a comparison between the Chamberta-2 model and a DMPNN trained for 8 different prediction tasks. This comparison is from the Chamberta-2 publication. You see 4 regression tasks on the left where lower values indicate better model performance, and you can see 4 classification tasks on the right where higher values indicate better model performance. And we can see that it depends on the prediction task which model performs better. However, if we look at the larger, more formal model, which, as we have discussed, seems to outperform the Chamberta-2 model, we see that the transformer network-based model achieves better results on all investigated prediction tasks. Potential reasons for why the transformer network performed better than the DMPNN might be that the transformer network can encode the stereochemistry of a molecule in contrast to the DMPNN model, and that on the other hand, the transformer network or networks were pre-trained on large data sets. While we could pre-train the DMPNN in a similar way, this wasn't done for these comparisons.